Minimum height trees looks innocent, until you try every root and blow up to ON squared. Bong interviewers love this because the optimal trick is stunningly simple. Peel the tree from the outside in until 1 to 2 centers remain. Master this, and you'll be ready for graph center/diameter problems on the spot. Let's attack it with basics. We're given n nodes labeled 0, n1 forming a tree, connected, acyclic, and an edge list. We need all node labels that can be roots producing minimum height. A tree's minimum height roots are exactly its centers, 1 or 2. Brute force, run BFS/DFS from each node to compute height ON squared. Instead, observe, if we trim leaves layer by layer, like topological sorting, the last 1 to 2 nodes left are the centers. Why? Because removing leaves doesn't change centers. We're shrinking toward the core. Complexity. ON time and ON space. Handle tiny cases. If n less than or equal to 2, return 0, n1. Build an adjacency list and a degree array. Initialize a queue with all leaves, degree 1. While more than 2 nodes remain, pop current leaves, reduce neighbor degrees, and collect new leaves. Return the last batch of nodes in the queue. They're the centers. Let's try to implement it using solution 1. Efficiency overview. The time complexity is big O of n, and the space complexity is also big O of n, where n is the number of nodes. This is highly efficient, as we only traverse the graph a constant number of times. Concept discussion. We are looking for the center nodes of the graph. The intuition is that the minimum height trees must lie somewhere near the center of the longest path, the diameter. We can find these centers by iteratively removing the outermost nodes, which are the leaves, layer by layer. This process is similar to peeling an onion. Since the maximum number of central nodes in a tree is 2, we stop when only 1 or 2 nodes remain. These remaining nodes are the roots of the minimum height trees. We start by defining the function and handling the simplest edge case. If there is only one node, that node is the root of the MHT. In the next step, we set up our adjacency list representation of the graph, which allows us to quickly look up neighbors. Simultaneously, we initialize an array to store the degree of each node. We iterate through the input edges to populate the graph and calculate the degree for every node. The process begins by identifying all the initial leaves. In a tree structure, a leaf is defined as any node with a degree of exactly 1. We load all these initial leaf nodes into our queue for the first round of trimming. This loop drives the entire trimming process. We continue removing layers of leaves as long as more than 2 nodes remain. Since minimum height trees can have at most 2 roots, once we reach 2 or fewer nodes, the centers have been found. Inside the loop, we process all leaves currently in the queue, representing one layer of the graph. We decrement the count of remaining nodes by the size of the current leaf layer. The next queue will hold the new nodes that become leaves after the current layer is removed. For every leaf being removed, we iterate through its neighbors. Removing the leaf effectively decreases the neighbor's degree count. If a neighbor's degree drops to 1, it means that neighbor has just become a new leaf, and we add it to the next queue for the next round of trimming. Once the while loop terminates, the queue contains only the remaining central nodes, 1 or 2. We return this queue as our final list of minimum height tree roots. And that's how this algorithm works. It first sets up the graph and identifies initial leaves, then gradually trims the outermost leaf layer until only the 1 or 2 central nodes remain. Efficient, simple, and elegant. Now that we've implemented our solution to find the minimum height trees, it's time to test it with an actual input. This helps us see how the algorithm trims leaves from the tree level by level to identify the root nodes that produce the minimum height. We'll walk through the input, observe how the leaves are removed, and confirm that the output matches the expected result. Let's test the function using this input. We have n equals 4, representing 4 nodes labeled from 0 to 3, and an edges array defining the connections between them. This tree structure forms a star centered at node 1, which connects to nodes 0, 2, and 3. Here's why the solution works. The algorithm builds a graph and counts the degree of each node. It then identifies the initial leaves, which are nodes with only one connection. One layer at a time, it removes these leaves and updates the degrees of their neighbors. This process continues until at most 2 nodes remain. Those remaining nodes are the roots of the minimum height trees. For this example, the initial leaves are 0, 2, and 3. After trimming them, only node 1 remains, which is the root of the minimum height tree. And that is exactly what the program outputs. 1. This verifies that the code works correctly and passes this test case. So our implementation is correct. The algorithm successfully identifies the center nodes that minimize the height of the tree. It handles the given structure accurately and returns the expected output. The BFS-style trimming ensures efficiency and guarantees that the minimal height roots are found. Let's try to implement it using solution 2. Efficiency overview. The time complexity is big O of n, and the space complexity is also big O of n, as we perform two breadth-first searches over the graph. Concept discussion. This solution utilizes the property that the root of a minimum height tree must always lie at the exact center, or centers, of the longest path in the graph, known as the tree's diameter. We find this diameter by performing two breadth-first searches. The first BFS finds the furthest node from an arbitrary starting point, one end of the diameter. The second BFS, starting from that endpoint, finds the absolute furthest node, the other end of the diameter. Once we have the full diameter path, we simply identify the middle one or two nodes, which are our MHT roots. We start by handling the base case of one node. Then we initialize the adjacency list representation of our graph by iterating through all the edges. Next, we define our essential breadth-first search helper function. It takes a starting node. We set up a queue for traversal, a parent array to trace the path back later, and a visited array to prevent cycles. This while loop is the standard BFS execution. It systematically explores all reachable nodes layer by layer. Importantly, it ensures we record the parent of every node found, and the loop returns the last node visited, which is the farthest node from the start node. This is the two-step approach to finding the diameter. We start the first BFS arbitrarily from node 0 to find one endpoint of the diameter. Then, we start the second BFS from this endpoint to guarantee finding the opposite endpoint, which is the absolute furthest node in the entire tree. Using the parent array recorded during the second BFS, we trace the path backward from the final furthest node all the way to its starting point, the other diameter endpoint. This gives us the full path representing the diameter. Finally, we locate the center or centers of the path. If the path length is odd, there is a single center node found by integer division. If the path length is even, there are two center nodes. These center nodes are the roots of our minimum height trees. And that's how this algorithm works. It first performs two breadth-first searches to find the tree diameter, then identifies the middle one or two nodes of that path. Efficient, simple, and elegant. Before checking the output, let's understand the problem. We are given n equals 6 nodes edges equals 3, 0, 3, 1, 3, 2, 3, 4, 5, 4. The goal is to find all roots of minimum height trees, nodes that produce the smallest height when chosen as tree roots. Let's test our function with this input. Here, we have a tree with 6 nodes, connected as described by the edges. Here's why the solution works. Build the graph. Represent nodes as adjacency lists. Use BFS to find tree diameter. First BFS from any node, here, node 0, finds one endpoint of the diameter, Nadia. Second BFS from Nadia finds the other endpoint, Nodeb, and keeps track of parent pointers to reconstruct the path. Identify middle nodes. The diameter path is the longest path in the tree. Nodes in the middle of this path are the roots of MHTs. If the path length is even, there are two middle nodes. If odd, one middle node. Step by step with this input. BFS from 0 farthest node is 5, BFS from 5 farthest node is 3, diameter path, 5, 4, 3, 0, or similar middle nodes, 3, 4. These nodes will produce minimum tree height when chosen as roots. And that is exactly what the program outputs, 3, 4. This confirms our code works correctly for this test case. So, our implementation is correct. It successfully identifies MHT roots, efficient, accurate, and reliable. Our implementation is correct. It accurately finds the diameter of the tree. It correctly identifies middle nodes as MHTs. Let's wrap up the minimum height trees problem. At first, it seems like you just need to pick the best root, but trying every node quickly explodes into ON squared. The clever trick here? We don't search from the roots outward, we peel the tree inward. Breakdown recap. We're given n nodes forming a connected, acyclic graph, a tree. Our goal is to find all possible root nodes that produce the minimum height when the tree is rooted there. In simple terms, we're looking for the tree's centers, the points that minimize the longest path to any leaf. Assess recap. The brute force approach would be to run BFS or DFS from every node to measure height, but that's too slow. Instead, we realize that the tree's centers can be found by trimming leaves layer by layer, just like peeling an onion. Each round, we remove the outermost leaves until only one or two nodes remain, which are the centers of the tree. Structure recap. We handled small cases first. If there are two or fewer nodes, we just return all of them. Then we built an adjacency list and tracked the degree of each node. Next, we added all current leaves to a queue, and while more than two nodes remained, we kept removing those leaves, updating their neighbors, and collecting new ones as they appeared. The final remaining nodes are our centers. Implement recap. After coding this peeling logic, we ran it on LeetCode, and the solution executed smoothly without any errors. Check recap. We verified it across multiple test cases, and each time, the output correctly identified the minimum height tree roots. Closing insight. The big lesson? Sometimes, finding the center of a problem means working from the outside in. By trimming layer by layer, we let the structure reveal its own core, efficiently, cleanly, and in linear time.